Thank you, Ishmael. I'd like to talk about something that I think Peter touched on nicely in the keynote today, is that one of the most interesting things we learned about in FIThydro when we built these new methods, tools, and devices is that maybe, just maybe, we need to start looking at things from a bit different perspective. So today I'd like to talk about downstream passage, not in terms of injury or mortality, not in terms of physical conditions and accelerations and velocities, but I'd like to talk about it in terms of what I call severity. From our measurements of 6 different European hydropower plants, we realized after about 2 or 3 years of processing the data and speaking with both hydropower plant owner operators and also with the fisheries biologists in this project and in others, that downstream passage is really not just about injury or mortality. It's not just about physical metrics. It's really talking about something which is severe. What do I mean when I say severe? Well, I actually mean a combination of 3 different things. The first and most intuitive sense of severity is severe physical conditions. So this is commonly thought of when we get, hit with the turbine blade, or when there's very large shears near a wall when a fish or a sensor are shot through the turbine. From a sensor point of view, severe physical conditions are challenging because they present us with the high risk of faults and even sensor loss. But after tens or even hundreds of sensor deployments through these hydropower turbines, looking at the data, and I did the analysis myself in most cases, I can tell you that we are also faced with severe uncertainty. We looked at multimodal, highly complex, multivariate sensors. So the acceleration was doing one thing and the rotation was doing another. And even after 50 or 100 deployments of sensors, it was oftentimes impossible to directly compare one-to-one those multivariate data sets. So we also are dealing with a very complex deterministic, things that we can predict by repeated measurement, and stochastic, the random, large-scale, chaotic nature of turbulent flows. And it turns out that passage through hydropower plants is a very complex balance of those things. And finally, as I mentioned earlier, we can only put so many fish and so many sensors through a hydropower turbine. This means that no matter how hard we try, we can't do thousands of case studies all across Europe to answer these things. So we have to come up with new methods that deal with severe sparsity. We need to deal with the reality that we will always have relatively low data coverage and availability. So today I'd like to talk about briefly is how we can begin to address and discuss the severity of downstream passage as a community. The biggest and I think largest source of severity during downstream passage is just the simple nature of the physical diversity associated with passing downstream in the first place. As you can tell from the simple graphic, a fish passing from upstream to downstream, it can not only pass through the turbine, can also go under a gate or over a weir. And there are a multitude of things, events, severe events that can occur to the fish. They can have pressure, they can collide with objects, they can also be exposed to fluid internal processes like high shear. That's when the velocity of the fluid, for instance, near a wall is low, but the velocity further away is high, and the fish can get spun out, or it can even cause injury. And then finally, we do have turbulence. Turbulence doesn't usually occur during the passage through the turbine itself, but over a gate, weir, and certainly in the tailwater and stilling basin, we've observed some very large-scale turbulences. So all of these things together paint a very complex, and I like to say diverse picture of where severity comes from. To give you an idea about the physical severity, in the FIThydro project, my group was tasked with building these 2B plastic sensors. It's basically a 12-centimeter long polycarbonate tube, and inside it has an inertial measurement unit that measures the linear velocity, angular velocity, magnetic field, and we also have 3 pressure sensors so that we can measure and correct very precisely those pressure signatures as they travel through the turbine. So the picture that we're looking at here is a very typical vertical axis Kaplan turbine passage event. The red line, the horizontal line, represents the atmospheric pressure, so the air pressure when you're standing outside the turbine. And we can see here, this black line represents the pressure as recorded by the sensor itself. At the beginning, the pressure is the same as atmospheric pressure. And as we inject our sensor into the turbine, the pressure goes up and then drops very, very sharply as it passes through the turbine and into the draft tube. And here alone, we have two different kinds of pressure events. We have these rapid pressure changes, and we have this low pressure minima, this so-called nadir pressure. So what I'd like to point out is here we actually have two different pressure-related physical conditions that can cause different kinds of severities. And recording those nadir pressures after about 30 to 40 measurements, we can get a statistically significant nadir pressure. But the rapid pressure changes themselves can vary widely and depend more precisely on the exact path a certain sensor or fish has taken. We also have strike events. So the fish and sensors, they can hit walls, they can scrape up against obstructions also in the downstream. So strike doesn't just mean getting hit by the turbine blade itself. And there are literally dozens or more locations where strike can occur. Finally, I'd like to point out that high velocities occur throughout, also in the tailwater. And so this diversity of physical conditions as experienced by our sensors, I think point out a very complex case and why we shouldn't talk about single events, but rather severity per se. And then finally, also, another source of severity is our uncertain knowledge about the different effects that fish anatomy, that is the structure of their body, and physiology, how they interact with the environment, how those also play important roles. And for instance, in the large Archimedes screw in Ham, Belgium, we found very clear differences between bream, eel, and roach, although the physical conditions were nearly identical. So one of the partial solutions that we've been working on at Taltech with our partners in FIThydro is coming up with new aggregated evaluations. On the horizontal axis, what we really see here are three different pictures of turbine, the operational conditions of the large Archimedes screw, from low rotational speeds, A, B is medium, and C is high. And what we did was we actually pooled all of the sensor deployments for each one, and then we plotted a probability of occurrence over the passage duration time. So now we have a more complete picture of a statistical likelihood of a certain event occurring over the total passage duration. And this gives us, I believe, a much more discretized in time evaluation of what kinds of events are occurring. And we can drill down through all of the different variables in order to find out maybe certain events are occurring in certain percentages of the passage. And then it's much easier for us to hone in and find out how, as Peter pointed out, maybe there's some operational adjustments that can be made to improve the fish friendliness of a given installation. The other solution that we have, and we've begun this last year in a new project, is the creation of new sensing technologies themselves. So one of the first things that biologists told us were plastic tubes are nice, but they're certainly not fish. And so what we've been working on in the last year and a half with our colleagues in Magdeburg is the development of new kinds of sensors that can be put on live fish themselves. And for more information, please also check out the Retaro project. So I'd like to conclude by saying that we can begin discussing and dealing with severity. So in terms of severe physical conditions, instead of using plastic tubes and then trying to relate them to fish, we can actually use recordings on live fish and cut out the middleman when possible. Dealing with severe uncertainty, I think that we need to really start looking at pooling or aggregating data, not only for one site and operating condition, but also across sites. And this will also, by pooling sites and standardizing the way that we do these measurements, this will also help us deal with the sparsity. So I'd also like to thank, on behalf of myself and my team, for supporting us. And our sensor technologies are now used in 10 different countries around the world, and we are in discussion with 2 more to join. And I think that FIThydro has really been a true international pan-European success story. Thank you very much.